differential area, take some moment to write down the first one. For example, write it for yourself. How to properly express DSR. Remember, surfaces are all vectors. Your differential surface in the R direction, what do I mean? This one, for example, this guy. Right? This guy, this area is having a surface normal pointing in the R direction. Right? In the R direction. Again, once you know its direction, the area must be determined by the other two differential lengths. So you need to have differential length in the phi direction, R, d phi. This is the differential length in the phi direction, multiplied by the differential length in the z direction. Okay? So you can try it for ds phi, ds z. I'm trying to repeat this process so you can fully understand what I mean. The essence is a surface in vector analysis is a vector. It results from vector cross product. Okay? Of course, you have the answers in front of you. So when we talk about ds phi, this is the simple case because the direction is in the phi direction, right? So the area must be determined by the differential length in the x and z direction. X and z are both not angular, so you don't have arc. So it's direct multiplication of dr and dz. Right? On the other hand, when you have a differential surface in the z direction, dsz direction is in the z direction, so the magnitude must be determined by the differential length in the phi direction multiplied by the r direction. So you have to be very careful. When you have the phi direction differential length, it is an arc. An arc is radius dependent. So you see this, these two are having radius dependence, but not this one. The surface pointing in the angular direction, the size is not radius dependent. Okay? You don't see the radius. Alright, so differential value, multiply them together. You multiply this one, and this one. You have the differential value. So are we clear up to now? I'm taking this extremely slowly. And the reason is, to me, the ability to fully understand and not having to memorize the formulation for gradient, divergence, and curl relies on your understanding to the most basic fundamental definitions. Right? So hopefully today, by the end of the day, I can show you why I'm focusing on this so much. Right? Now you have to think, well, eventually, a given point is a point. Right? For example, this point is this point, but I can freely determine whether I want to express it using Cartesian coordinate or cylindrical coordinate. It's my choice. The point does not change. How to express it can be changed. So the question is, are we able to freely convert or transform that given point coordinate by using Cartesian or cylindrical definitions? Right? So I'm now showing you the relationship of the four unit vectors. X unit vector, y unit vector, r unit vector, and phi unit vectors. I'm showing you this 4. Why only this 4? Because z are both common. Z are identical for Cartesian and cylindrical coordinates, so they don't need conversion. This is the point you need to rely on your understanding and ability for performing inner products, dot products. R unit vector might be making some angle phi with x unit vector. Okay? So the meaning of dot product is to find the projection, right? If you want to express the r unit vector as x unit vector and y unit vector, you only have to project them. Project it onto both. Okay? So if you want to project the r unit vector onto x unit vector, you have cosine. And the r unit vector as projected onto the y unit vector is taking sine phi. Okay? So that's what's being listed here. So r unit vector making a dot product under this definition of phi. The phi is the angle with x axis, always. Okay? Phi is defined as your radius making the angle with the x-axis. And therefore, if you want to make the inner dot product or find the projection of r unit vector onto y, you have sine phi. So these are extremely important because understanding this allows you to convert between the two coordinate systems. On the other hand, phi unit vector, when it projects onto the y unit vector, is straightforward. You take the cosine. But y projected onto the x is now having a negative sign, right? Positive x is defined downwards, but you see this a phi is pointing upwards. So it is having a negative sign, and it takes a form of sine rather than cosine. So a phi projected onto x unit vector takes on a negative sign in the form of sine phi. But a phi projected onto the ay unit vector, straightforward, just cosine phi. So whenever you are on your examination or in the future you're trying to do some derivation, you have to be able to draw these 4 unit vectors. And everything is straightforward. You don't have to memorize anything. Okay? But just for your reference, let me write down these 2 equations for you because we are going to use it in the future. Okay, we are going to use it in the future. So being able to convert or transform from one coordinate system to the other is nothing more than just understanding the basic definition of a given orthogonal coordinate system. Okay. And then you can compare the unit vectors between 2 systems. And then you can just really convert. Okay, so let's come back to the PowerPoint. Let's try to convert the positions. Okay. Suppose I know a position expressed using cylindrical coordinate. Can I transform it into the Cartesian coordinate? when I first express a given point in cylindrical coordinate, it means I know its radius, I know its azimuthal angle, I know its height, z. But somehow I don't like it. I want to express it using x, y, z. Is it possible? Of course, if you like it, you can do it. So let's understand about this point. So this point, we know its radius, we know its azimuthal angle, so we know how to express its corresponding x value and y value. X is just r cosine phi, y is r sine phi, right? That's all you have to do. So now you can convert the point initially expressed in cylindrical coordinate, but now using these expressions, right? It's now in Cartesian coordinate. Likewise, when you initially define a point in Cartesian dimensions, you can also change it to the cylindrical coordinate. Because once we know the points x, y, and z, this r, the radius, is just x squared plus y squared, and take the square root. And phi is just the ratio of y to x, and you take the tangent arc. Okay? Z remains unchanged. So these are extremely easy. Changing between the point position between two coordinate systems are straightforward. But what about the vectors? Take a good look. As I mentioned, a vector can also be expressed using whatever orthogonal coordinate system you like. Okay? So what I'm saying is, this A, vector A, can be written down in the form of Cartesian coordinate, but it can also be written down in the form of cylindrical coordinate. It's the same vector, but only expressed in two different ways. So for example, if I already give you the vector expression using Cartesian coordinate, like the one I wrote on the blackboard. All right, let's walk to the blackboard. I initially gave you the proper expression of ax, ay, and az. So basically, I defined the vector, but using Cartesian coordinates. So you see a lot of x, y, y, z, and y squared, right? But they are not proper as the expression for cylindrical coordinate. So you have to convert. So how to do the conversion? Again, I'm showing you this. The proper conversion relies on your understanding of the relationships among the four unit vectors, but which is already here on the blackboard. I copied it down for you. But what is the methodology? How should we approach this problem? The ones in blue is something you know it already. Okay? Suppose I gave you the vector expression in Cartesian coordinate. How can we find out the resulting AR, A5, and AC? So this is the point you really have to think and try to understand the basic meaning of orthogonal coordinate systems. What if I make a dot product to A happens if I use one of the unit vectors and I make an inner product with A. For example, if the entire A vector is making an inner product with AR, I would extract this AR component, right? Because by making inner product of the radius unit vector, these two vanishes, right? These two are just gone. They're orthogonal. You only extract this component. Okay? So I know how to extract the AR component. This is what I want to have, right? I want to transform the vector in Cartesian coordinate into the cylindrical coordinate. So I need to be able to write down AR, A phi, AZ individually. So the process, I extract this one by making an inner product of R unit vector to A. So on the right-hand side, I only have AR. But for the blue stuff, this is a direct inner product of my original vector expressed in Cartesian coordinate, but now making an inner product with the radius unit vector. So this is where the transform begins. Okay? So smart students, when you perform this inner product, how many terms do you have? Ideally, you would have 3 terms, but in the end, because R unit vector is orthogonal perpendicular to Z, so in the end, this one is not there. So all you have is AR component is now contributed from the sum of AX plus AY components, but with certain scaling factor. And those scaling factors, we already know. Why? Because I'm such a nice teacher, I wrote down this for you, right? I taught you, and I wrote it down for you. Because R, X, Y, all the relationships, all the inner product, all the projections are known. So R unit vector making inner dot product with X unit vector is cosine. R unit vector making the inner product or the projection onto the Y unit vector is sine phi. Okay. So if you can compare the PowerPoints and the Blackboard, this is what I emphasized. All the conversions relies on your understanding, your deep understanding to the 4 unit vectors. Once you know their relationships, you know how to do the conversion. So that is AR component is coming from both AX and AY, but with a strange fraction of scaling factor. AX times cosine phi, AY times sine phi. Okay? We can repeat the process to extract A phi. Do we need to extract for AZ? AZ? They are the same, right? They are the same, so you don't have to extract. When you're trying to transform from Cartesian to cylindrical, or cylindrical back to Cartesian, you don't have to worry about the Z component because they are identical. So we can repeat the process to extract the A phi. How to extract A phi component you only have to make inner dot product. Okay? The dot product of the entire vector with phi unit vector. Right? So you only extract this chain. And that's equivalent to saying the Cartesian vector is now making an inner product with phi unit vector. But that we already know, right? We already talked about it. So, phi unit vector projected onto x unit vector is negative sine phi. This one is cosine phi. Okay. So in the end, there's a very simple table or matrix form allowing you to do the transformation. If you know your vector in the form of Cartesian form, you just write down ax, ay, and az, and then multiply it by this matrix, and then you have ar, a phi, az. But remember, you have to express all these x, y's, y, z, y squares using also the transform way. Right? So x is r cosine phi, y is r sine phi. So let's just do this for you. R equals, so x is r cosine phi multiplied by r sine phi, and then multiplied by cosine phi. So it's squared. Right? Ay is y times z. So it's r sine phi times z. But you have to multiply the additional sine phi. Okay. Az is y squared. But when you transform the vector into a new coordinate, you don't want to see x and y, right? So this is r sine phi squared. Simple. But ask yourselves, can you get it right if we have an examination in 10 minutes? Probably you get 0 points. Okay? So try to absorb what I taught you up to now. Okay? Let's take a 10 minutes recess. But during this 10 minutes, try to think, what is my methodology? I'm merely using the definition of orthogonal coordinate systems, the unit vectors. I'm only trying to draw these 4 unit vectors, and that already allowed me to freely transfer between the two systems. All right?